we're going to do lesson 11.7, modeling data with exponential and logarithmic functions. It says that the doubling time or amount of time t required for quantity modeled by the exponential equation n equals n sub 0, that's the initial value, times e to the kt to double is given by t equals the natural log of 2 over k. What that means is, in order for something to double, so n would be the value that it is when it doubles. You've got the initial value. Let's say the initial value is 500. Doubled would be obviously 1,000. K is some constant, we don't know. Again, E is that number 2.8, blah, 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 and T is time, okay? T is the time that it takes for it to double. And that's what this second equation is, where the natural log of 2 means double, and K is the constant that the time is multiplied by in the first equation, okay? So we have an example. It says Tara's parents invested $5,000 in an account that earns 11.5% compounded continuously. They would like to double their investment in 5 years to help finance Tara's college education. So A says, will the initial investment of $5,000 double within 5 years? We have our exponential equation, which is n equals, or it's the basic form really. And the formula for continuous compounded interest is A equals P times E to the RT. It should look a lot like the first equation that we have here. So the principal, which is the original amount that you invested, is the n sub 0. You can see we've got the E there. The K, or the constant, is our rate, and then we've got the T for time again. So what we know is that K is really equal to R here. It wants to know if the initial investment of $5,000 will double within 5 years. So let's see. We've got the amount. That's going to be, we want to see if, is it going to be $10,000? Because that would be to double the 5,000. 5,000 times e to the, remember it's RT. R is the interest. The interest is 11.5%. So that's 0.115. That's the interest rate. Times T, which is in years. So that's 5 years. And we just want to see if that's equal to $10,000. What we find out is that A is actually equal to $8,885.65, which is obviously not $10,000. So it won't double, at least not in 5 years. So then kind of the question is, well, when will it double? To do that, we're going to take that time, that second time equation that's given at the top of the page. It says 2 equals the T equals the natural log of 2 over K. Remember that K is the interest rate. K and R are the same thing for this particular problem, so it's only specific to this problem. We're going to figure out what the time actually is going to end up being for it to double if the interest remains at 11.5%. And we find out that T is approximately 6.03 years. So We really need another year invested before the investment of $5,000 will double. Right, the second part of that problem, part B, it says what interest rate is required for an investment with continuous compound interest to double in 5 years. So again, remember that R, or K equals R. So K, the constant in the first equation, is equal to R, which is the rate in the second equation. And so I'm going to use my time function again, time over the natural log of 2 over K. We want to know what is K, or R in this case, in order for it to double in 5 years. So if T is 5, what's K? Remember, K is our rate. So we put 5 in for T. The natural log of 2 over K. You can do a little cross multiplying here. Multiply both sides by K. So you get 5K equals the natural log of 2. And then divide by 5. So K is the natural log of 2 over 5, which is equal to 1.39, or 0.139, and that's 13.9%. So in order for it to double in 5 years, we have to have an interest rate of 13.9%. All right, on the second page, we have a little word problem here, and this is going to use an exponential function. It says exponential regression can be used in the experimental determination of the half-life of a radioactive element. A scientist starts with a 10-gram sample of uranium-239 and records the measurements shown below. It wants us to find a regression equation for the amount of uranium as a function of time, which is x. I'm going to show you how to use Desmos for this, and we're going to ask Desmos to make us an exponential function. So I go to Desmos. I've got what I'm going to do first, so you guys can kind of do this along with me, is I'm going to go to the plus sign, and I'm going to enter my data as my x and y. So x is going to be my time, which is for my x, so 0, 5, 10, 15, and 20. And I want to delete those other values. And then I want to put in my Y1 values, and those are my grams of uranium, which is 10, 8.6, 7.5, 6.3, and 5.5. Okay, after I get my table of values in there, I'm going to go to my next line, and I'm going to ask it to write an equation. Well, we can take just a look here to see if our points are plotted. There we can start to see them. The points that we put in our table are there in red. So I'm going to ask it to write an equation. To do this, I have to go up to the plus sign, and I'm going to ask it to write an expression. Now this is where it gets kind of sneaky, because our input values are not just x and our output values y, it's x sub 1 and y sub 1. So when I ask it to write my equation 1, I have to know what equation I want to write. For this one, it did say that it's an exponential regression. An exponential equation is in the form y equals a times b to the x. Now in this case, what we want to do is put y sub 1, because in our table the y's are listed as y sub 1 and x sub 1. It's a little bit tricky here. We're going to go y and just hit 1, and it should say y sub 1. Now we're not going to hit equals. We have to have this little squiggle sign. So instead of equal, we're going to make a little squiggle like that. We're going to hit the ABC button, and at the very bottom, there is a squiggle. That is going to tell Desmos that we're writing an equation based on the table of values. And then you can go back to your original, I guess you need to go back to the letters and say A time and then B. Go back to the main screen on Desmos and put in an exponent of x sub 1. Once you do that, it gives you your function. It tells you, just like our graphing calculator did, what the A is and what the B is in our function. And you can see that it graphed it on there. So the equation of that exponential function is y equals 10.001 times B, which is 0.9703 to the x. That's the equation. So that's what we want to put for part A in the problem. I'm going to go back to our notes real quick. So for A, we have an equation that says y equals 10.011 times 0.9703 to the x power. Part B asks us to write this regression equation in terms of base E. What that's going to look like, remember, we can have y equals e to the x. We're going to base it off of that, so that's base E. The thing that has the exponent on it, this 0.9703, we're going to write it in terms of E. So to do that, we want e to the x to equal 0.9703. And I'm going to put that in log form so that I have log base E of 0.9703 is equal to x. Remember that log base E is the natural log. So the natural log of 9703 is equal to x, and that makes x equal to negative 0.0301. Now what I'm going to do with that is substitute that in for .9703. So that tells me that e to the negative 0.0310 is equal to 0.9703. 9703. And that is going to go up here. So that I write it x or with log base or with base e. Y equals 1010